Number one, the number of grams in 2.58 moles of sodium carbonate. Okay. And like I said before, when you work, when you're trying to answer these problems, the best thing that I found is to extract information from the problem and put it on the paper, on the board, whatever your writing medium is, and divorce it from the prose of the problem. Because test questions, word problems especially, are designed to confuse. They throw information in there that you don't need, or they leave information out that you have to go find. So it's helpful to extract the information out of the problem and then work the question. So we're looking for the number of grams of that sodium carbonate. So how are we going to get there? If we're going from moles to grams, right, we need something that will convert that to the other one, right? So dimensional analysis says you need to cancel moles and leave with grams. Okay, there's a clue. Grams and moles in a quotient should say to you immediately, molar mass. That's how much a mole weighs. So what else are we given? We're given sodium carbonate. You're given the name of the compound. You're not given the formula. And the formula is what you need to determine that value. So sodium carbonate, we know it's got sodium in it. And carbonate, you won't find that on the periodic table, right? Because it's a polyatomic ion. So you have to know what it is, or useful information. Let me be sure it's there. Because if it's in the review document, it'll be on the exam. Yeah, polyatomic ion. There's the whole list of them. So you should look down there for carbonate, and you find that it's CO3, and you also find out what charge it is. Because you have to balance the charges in order to write this correctly. So if that's 2 minuses for this group, then you need 2 of these to balance that charge. And you don't need those charges from now on. But that's the formula, and that's what you need to determine the molar mass of this compound. So how do we do that? Well, you add up the molar masses of the individual elements. Well, you've got 2 sodiums, right? If you look on your periodic table, sodium is, and I always round off to 2 decimal places, which is perfectly adequate. You see where it is? Yeah, and you see the molar mass, and it goes out 22.98977. I round off to 23.00. So 23.00, but you need 2 of them. Okay? And you need 1 carbon. I have that one memorized. And you need 3 oxygens. I have that one memorized. That's because, not because I just sat down and memorized them, but because I use them over and over and over and over again. They just stick. Okay, so now we just need to do our calculation. What's the molar mass of sodium carbonate? Let's see, I do that one 46 in my head, and then 12.01, and then 3 times 16 is 48. Okay, I get 106.01. 106.01 grams per mole. And this is in the same quotient relationship as that one, so we put 106 on top per mole. Now we have our conversion factor, and we can find out how many grams of that compound this represents. I still got it in my computer, in my calculator, so I'll just say 2.58 times that value. Okay, I get 273.5058. 273.5058. And for answering the question, that's probably good enough, but if we're going to use significant figure rules, this one is an exact number. Right? All conversion factors are treated as exact numbers. So we only have to say 3 significant figures here, 3 there, 274. Round it off. And there it is right there, D. Well, it should be D because the key says it's D. But I have caught mistakes before. So it's good to, and it's good practice for me too, just to do the whole thing through. Because chemistry is a perishable skill. If you don't use it, you'll lose it. So hopefully, the next classes that you take, you'll need chemistry. And you can use what you've learned and master the next one. Okay, how about 2? 8.52 grams of water, 8.52 grams of water contains how many molecules? Okay, so we're going from there to molecules. Okay, so we need a conversion factor. Well, there are no conversion factors that go straight from grams of water to molecules. So this is going to be a chained conversion. So think about it this way. You're going from mass to numbers. So how do you bridge the gap between mass and numbers? Well, the only relationship we know that goes from mass to any kind of numbers is molar mass, grams to moles. Grams is mass, moles is numbers. So if we do our first conversion like this, that'll give us in the neighborhood of moles, and then we know that the relationship of this many numbers to that many numbers is Avogadro. Okay. And that'll get us to molecules. But first, we got to figure out what this one is. So everybody knows what water is. Should know. A2O. That deadly poisonous chemical, dihydrogen monoxide. So 2 hydrogens is what? Well, it's 2.02 because it's 2 times 1.01. You get that from the periodic table also. And then oxygen is 16. So it's 18.02 grams per mole. 18.02. Notice it goes on the bottom because we have to cancel these grams and leave us with moles. Okay? That's what I call the thinking part of the problem. The rest is number crunching. So we just take 8.52, divide by 18.02, multiply by 6.022, 10 to the 23rd, and I get 284725, 284725, times 10 to the 23rd. Right? Conversion factor, that determines significant figures. So we round off to here, 2.84 times 10 to the 23rd. Oops, excuse me, I need to round correctly. That's a 7. 2.85 times 10 to the 23rd. Okay? Now, if I lose you in this process, speak up. Okay? I don't want to erase something while you're trying to copy it down.
You're good.
Even though it is recorded, I mean, it helps the learning process to have as many stimuli coming in as possible. You see it, you hear, and you write it down. And those different pathways reinforce it in your brain. And then, of course, struggling with a problem is the best way to learn it. I mean, the stuff that you struggle with are things that you remember long-term for decades. Like stuff in high school that I missed on tests and quizzes, I never forgot them after that. Okay, 3. I don't know if I told you guys. One question. What was the battle tactic that the Nazis used during World War II that made them so successful? Blitzkrieg. I missed it on a test. Never forgot it after that. Okay, how many moles of Al2O3, okay, we're given that one, are present in 78.8 grams of the compound. So we're given 78.8 grams of Al2O3. And the question is, how many moles? Right. First of all, is that correct? I mean, whoever creates these questions, they might be sneaky enough to put the wrong formula in there. Don't take them at their word. Is that correct? Well, oxygen is -2, right? It's a chalcogen. Right? In that family, they're all, when they're in ionic compounds like this, they're all -2s. How about aluminum? Aluminum, you got alkaline metals are +1, alkaline earths are +2, and then you skip over the transition metals because you're above them when you go over here to aluminum. Aluminum is +3, +1, +2, +3. +3. Yeah, that's right. Cross multiply. 3 over here, 2 over there. Gives you a 6+ and a 6- charge. They balance. Okay, so we've confirmed that. And even if they're not sneaky, they might make a mistake. You know, typographical errors are common. Okay, so now we've got this many grams of that compound. We need to go to moles. So if we're going from grams to moles, we do know a relationship that'll do that. And we've already talked about that. Right? Cancel grams, leave you with moles. We just need to leave the molar mass of aluminum oxide. Now, am I calling that by the right name? Yeah. Aluminum only has 1 charge. So it makes it a type 1 compound. We don't have to say aluminum 3 because there's no other possibilities. It would be redundant. So aluminum oxide is the correct name for that. And we just need to figure out what is the molar mass of aluminum oxide. We know 2 times aluminums. We have to look up aluminum. 7? Rounded off 26.98. You could probably deduce the right answer here from 27 because you have choices, you know, and only one of them is probably going to be close enough. What I say, 26.98, and then 3 oxygens, 16.00. So now we just whip out the calculator and then add oxygen to it. 101.96. 101.96. 101.96. That divides into this. And I get 0.772852 moles. Well, we can only keep 3 of them. So it's 0.773 moles. Did I do that right? Oh, I'm looking at the wrong one. Yeah, 773. There you go. Okay. I'm going to pick up the pace if we're going to get through all these. Let's see if I can page. Yeah, 4 and 5. Okay. About 4. Which of the following compounds has the greatest percent by mass of oxygen? Ooh, okay. The question is percent mass for oxygen. The greatest. So how are we going to do this? Henry Ford, set up your assembly line. We've got A, B, C, D, and an E. Okay? We've got these different compounds. Potassium carbonate. So we have to write potassium and carbonate. 2 minus charge plus 1 charge. Need 2 of them. Nitric acid. Right? We know all acids start with hydrogen. And the naming convention is if we don't have any hydro in it, that means there's oxygen in there. So nitric, X derived from A's. So we need nitrate in that acid. This is -1, that's +1. So that one is correct. About zinc 2 oxide. Zinc has a 2+ charge. Oxygen has a 2- charge. That's it. 1 and 1 is the proper ratio. Sulfur dioxide. All right. What type of compound is that? Sulfur and oxygen. It's type 3. Right? So it just tells us how many there are. Sulfur, 2 oxygens. Diphosphorus pentoxide is another type 3. Diphosphorus pentoxide. There you go. Now you got all your compounds written. The next thing is, which one has the greatest percent by mass of oxygen? Well, if we're going to do percent by mass, we talked about that Tuesday. You need to ratio the molar mass of all your oxygens to the molar mass of the compound. So in the denominator and the numerator, you're going to have 3 oxygens here. But then on the bottom, you're going to have to add carbon and 2 potassiums. Potassium is 39 something, I believe. Yeah, 39.10. Okay, we do the same thing for each one. Right here, we got 3 oxygens again. Okay, and now we're going to add nitrogen and hydrogen for the total. Zinc. Zinc's a transition metal. So it ought to be 65.39 here. But we have to add oxygen here and oxygen here. There's only one of them. Okay. Let's see, I'm going to have to scoot down a little bit. The next one. 2 oxygens and 2 oxygens. Plus sulfur. Sulfur is 32 something. 3206 for sulfur. 32.06. And then for this one, we have 5 oxygens. And then 2 phosphorus. 30.97 for phosphorus. Okay. Now, if we're actually going to calculate percent, we got to multiply each one of these by 100. There we go. Now, the rest, as they say, is history. 1, 2, 3, 4, 5. So we got them all. This is Henry Ford in action, assembly line. So now we've got, let's see, 48, and then add 12.01 and 2 times 39.10. That. So I get 48 divided by 138.21 times 100. So that's 34, let's see. Well, actually, we're doing comparisons, so significant figures aren't as important in this case, because we just want to find out which one's got the most. 34.73. Okay, how about this one? All right, 48, 3 times 16. And then 14.01, 1.01, and let's see. I want to do that again. I did some fast checking in my head and I didn't like what I was coming up with. There we go. So now I get 76.17. Okay, how about this one? Let's see, 16 and 65.39. I get 19.66. And then sulfur dioxide. Let's see, 2 times 16, 32. 2.06. And then I get 49.95 here. And then the last one, 16 times 5, which is 80. And then I got to add the phosphorus. Okay. And I get 56.36. Okay. So which one has the greatest percent by mass of oxygen? Nitric acid. Okay. There's no way you can reason that in your head just by looking at the answers. Best you can do is a wild guess, unless you actually go through and calculate each one, because the number of oxygens don't matter. This one's got 3. That one's only got 1. It should be the least. And by coincidence, it is. But this one has 5 oxygens, but it's not the greatest percent. Okay, that was 4 compliments of Henry Ford. Okay, 5. All right, compound X2Y is known to be 60% X. Calculate the percent Y by mass for X2Y2. Okay. That looks like a real hair puller, but it's not. if you extract the information so that you know what you're dealing with. Okay, the compound X2Y is said to be 60% X. 60% X. We have to be told this because X and Y are not real elements. So we have to be given that information. Then we want to calculate what's the Y percent for X2, Y2. X2, Y2. Y percent is the question. Okay, what does this tell us? If this compound is 60% X, and we know that it only has Y in it other than X, how much is X? I mean, how much is Y? Y has to be 40%. Okay? So, let's see. If we have 100 grams of this sample, and this represents 60 grams and 40 grams. Okay? With me so far? All right, parts per 100, right? 60 grams per 100. So, if we take the same two X's and put them over here, 60 grams, and then we take 40 grams here and double it, right? 80 grams, one Y represents 40 grams, and two Y's represent 80 grams. Now we have 140 grams total. Well, what percent is 80 of 40 of 140? 80 of 140 is 8 divided by 14. Which is 57, approximately 57%. Why? Okay. So that's why it's D. Okay. Let's see which one's next. Usually I don't like those X and Y's and the A's and B's. I'd rather work with real chemicals, but sometimes they're useful. Okay, let's get that one, that one, that one, that one. Oh, there's 12. Let's see. It's 13. And E. Yeah, it does. Let's scroll up to that one. There we go. 12. What's the mass of 5.826 moles? 5.826 moles of calcium hydroxide. Is that correct? Calcium is an alkaline metal, an alkaline earth, excuse me, is 2+. Hydroxide is a polyatomic ion with -1. So yeah, 2 of those for each one of these. Okay, what's the mass of that many moles? Well, if we're going to mass, then we do have a conversion factor that will do that. It's called molar mass. So we just need, what's calcium hydroxide molar mass? Well, calcium is what? About 40.08. Calcium, 40.08. How many oxygens do we have? 2. How many hydrogens do we have? Also 2, because we have this subscript. Now we can find out what calcium hydroxide weighs per mole. I get 74.10 grams per mole. So grams is up here, moles there, and we just multiply it by 5.826 moles. And I get 4.3 17066. And we can keep 4 of them. So 4.317 grams. Is that a choice? Oh, excuse me. Check my calculator. 10 is 10 squared. So that would be 431.7 grams. There it is. All right, that's 12. $13. Choose the pair of compounds with the same empirical formula. Okay. So you got to remember what empirical formula is. The simplest whole number ratio of elements in a compound. So A is water and hydrogen peroxide. Can that be the same empirical? No. The empirical formula for that is just that. That's as far as you can go. But the empirical formula for this one is HO. It can be reduced further. Right? So that one's not it. How about B? C2H2 and C6H6. And notice that you have unique answers for every one. This is test-taking technique for multiple choice. So if you start at the top, work your way down. When you find the answer, you can stop. You don't have to go any further. So the empirical formula for this one is CH, right? Divide by 2. And the empirical formula for this one is CH, divide by 6. There you go. B is your answer. We don't even have to look at the rest of them. So as an instructor, I probably should have put this one maybe down here. Then you'd have to go through 4 of them to get there. Unless you are a contrarian, and then you start at the bottom and work your way up. Either way, once you find the right answer, you can quit. Assuming you have confidence in your skill. If you know you're doing it right, then when you get to the one that is right, you're done. All right, 13, 15. What's the molar mass of barium hydroxide? Okay. Yeah, we're going simpler now. So barium is a big atom, right? It's way down toward the bottom of the alkaline earths. 137.33. Right. 2 oxygens and 2 hydrogens. Carrying over 1. There. 171.31 grams per mole. Which one comes close to that? That was right on. So your answer is A. About 16. Calculate the number of molecules in 0.004000 grams of gaseous oxygen. Okay. The key to this one is not just how to make the conversion, but gaseous oxygen. What is gaseous oxygen? It's always diatomic. So that's the purpose of this question, to see if you remember diatomics. All right, so now we can convert that. Let's see, we're going to calculate number of molecules. All right, so we're going to go to moles first. So we need molar mass of gaseous oxygen. And then we're going to multiply, since grams cancel. Number of molecules. We need 6.022 times 10 to the 23rd mole. And moles cancel. Okay, so now we need 1, 2, 3, 4, and 32, and 6.022 exponent 23 times 7.5275 times 10 to the 18th molecules. And we can keep 3 of them. So it's 7.53 times 10 to the 18th. Which should be, let's see, we're 16. There it is, 7.53 times 10 to the 18th. Okay, 17. .6 grams of copper represents how many moles? Actually getting simpler. Grams of copper. Right? If we're going from grams to moles, that's simple. Molar mass of copper. So you just have to know where copper is. It's a transition metal. Right next door to zinc. Rounded off. 63.55. 63.55. And just divide that into 22.6. Now, is that going to be, let's see, that's going to be less than 1, right? Okay, how much less than 1? Looks like it's about a third, doesn't it? Like 0.3. How about that one doesn't get close, that one doesn't, there you go. 0.356. We don't need a calculator. So, if you have the presence of mind, I mean, if you're not too shaken by the fact that you're taking a chemistry exam, then some of these, since they're multiple choice, you can do them in your head. And all you have to do is estimate, get close, and say, all right, the instructor wasn't smart enough to put in 0.324. In which case you need to calculate it to get the right answer. So if I were sneaky, I should have put one in here that was close to this one, but not the right one. But at least on the review document, I didn't do that. Okay, 17, let's go to 19. Calculate the number of moles of chlorine molecules in a sample that contains 7.380 times 10 to the 25th molecules of this. And the question is, how many moles is that? This is simple. It just needs a conversion factor that will go molecules to moles. And we know what that conversion factor is. I got those numbers. Divide that into 7.380. Well, let's see. Can I reason this one? Let's see. This would be a little over 1, but that would be times 100. Right? 23 subtracted from 25 is 10 squared. So it'd be about 100. Probably this one. See that one? I better do it. 7.385 and then 6.022. I need to put that one in memory. So I have to keep typing it in. 123 or 122.6. 1, 2, 3, 4. 122.6. There you go. All right. That's 19. And let's scroll down to 22. 22. Okay. Acetylene gas is 92.3% carbon and 7.7% hydrogen by mass. And its molar mass is 26 grams per mil. What's the molecular formula? Right, so you remember the steps we have to go through. Right. Major steps. Empirical first. And molecular. Right? And the information you need to go from here to here is the molar mass of the compound. But to get to here, all you need is percent composition. You can calculate the empirical formula. But to go from here to here, you need the molar mass, and we have everything we need. Percent composition for the empirical formula and molar mass for the second step. Okay, so let's put what we know on the board. 92.3% carbon, it's acetylene. 92.3% carbon and 7.7% hydrogen. So next step. What do we look when we write a formula for a compound? What are we actually saying? We're saying in that compound, the subscripts of the symbols represent how many atoms of each one is in that molecule, which means numbers. We have to ratio numbers. We can't ratio mass, doesn't work. Well, that's already been done for us anyway. But in order to write the formula, we have to know numbers. And to go from mass, to go from percent to numbers, we got to know mass. Well, this doesn't tell us mass. Percent's dimensionless, unless you know that percent is by mass. So this is parts per 100, mass of carbon per 100 grams of sample, which means we assume 100 gram sample. Now we can say 92.3 grams of carbon and 7.7 grams of hydrogen. Now we can convert to numbers. Get rid of the grams, leave you with moles. There we go. So carbon is going to be 12.01. Hydrogen is going to be 1.01. And that'll give us the mole ratio of each one. 92.3 and divide that by 12.01 is, replaces, 7.69. 7.69 grams of carbon. And 7.7 divided by 1.01 is 7.62. 62 grams. Normally what you would do here is take the smallest one and divide everything through by it. But this is simpler. they're so close together, they're 1-to-1. Carbon, hydrogen. This is the empirical formula of acetylene. What we need to know is what's the multiplier to give us the molecular formula. So the next step is what? Ratio the true molar mass to the empirical mass. So what's the empirical mass? 12.01 and 1.01 is 203. 13.02 grams per mole of this formula. And given 26, this is the molar mass of the compound, 26 grams per mole. And this is 13.02 grams per mole of that formula. And this is equal to that ratio, which is about 2. So acetylene is going to be C2H2. Okay? All right, that was 22. And scroll to need to move this like that. 24. It looks like we're backpedaling, except you're given the name here, the molar mass of ammonium phosphate. So you have to recognize, first of all, that you need the formula for ammonium phosphate in order to answer the question. What's the molar mass of that compound? You can't do it from the name. You need the formula. And you also have to recognize that ammonium is not on the periodic table. Phosphate's not on the periodic table. It's in your ion, your brain farts. Polyatomic ions. Okay, so ammonium phosphate. Ammonium is this, right? With a +1 charge. Phosphate is this one with a 3- charge. So, since this positive is distributed over the entire unit, if we need more than one of them, we have to use the parentheses. And we do. We need 3 of them. 3 positives match a 3 negative. So that's the formula. Now you can calculate the molar mass. 3 nitrogens. How many hydrogens? 12 hydrogens. 1 phosphorus. 32O6 is it? No, it's 30. I'm thinking of sulfur. 30.97. Okay, and 4 oxygens. Okay, like I say, that's the thinking part. The rest is number crunch. 14.01 times 3. And then 12 times 1.01. Add that together, 30.97, only need one of them. And 16 times 4 is 64. So I get 141.12 grams per mole. And for 141, I made a mistake somehow. Let's see, 14.01 3 times, okay. 2 plus 30.97 and yeah, I did make a mistake. 149.12. Okay. Test taking technique. If you've got all these answers to choose from, and your answer comes after that, what do? Pick the best answer. Right? The closest one to this is E. Then you go on your merry way. That is probably a rounding error. 27. 26.4 grams of nickel represents how many atoms? 26.4 grams of nickel. Right? We can't go straight from grams to atoms. There's no conversion that'll do that. But we can go from mass to numbers in terms of moles. Right? And then we can go from atoms to moles. You know this one. We just need, what's the molar mass of nickel? So we go back to our periodic table. Next door to copper, 58.69. There we go. So all we have to do now is calculate. 2, 3. I'm going to put this in the memory. Store. And then 58.69. So I get 2.788. 2.788 times 10 to the 23rd, I believe. Yep. We can only keep 3 of those. Right? 2.79 times 10 to the 23rd atoms. Did I make a mistake in my calculations? Yes, I did. I rounded wrong. 7 must be 7 0. Yeah, 708. Okay, so the answer is B. Okay. 31. What's the mass of 8 atoms of copper? Okay, you're given 8 atoms of copper. What's the mass? Well, this is the problem before it in reverse. Now we're going from atoms to mass. You can't get there directly. You have to chain it together. Right? Make moles out of it first, then cancel the moles with molar mass. Right? So the atoms are gone, moles are gone, we're left with grams. So what's copper? Yeah, 63.55 grams per mole. There we go. So now we just say 8 times 63.55 and then divide by Avogadro's number. Let's see if I can recall it. Nope. It's not cooperating. I have to punch it in. I get 8, 4, 4, 2, 3, 7, 8 times 10 to the minus 22. Oops. Okay. Here's a good lesson. 8 is a counting number. It's an exact number. Right? 8 has infinite number of significant figures. So I could keep all of those if I want to. and then compare them to the answers, right? But if this were a fill in the blank or show you calculation, you'd be justified in giving that entire number as your answer, because this is an exact number, that's exact because they're conversion factors. And that's the exact number because it's a counting number. Like, what was it, 9 pencils, 8 atoms. So we could keep this one. But since it's multiple choice, then you compare that to what you have to go on here, and there's your best answer. Okay? All right, 31. You probably noticed 42 was crossed out. If you had a chance to look at the review document. The reason I did that was when I first put this review document together, then I did the handwritten worked problems, and they were numbered in order. And rather than go back and redo the whole thing and renumber them, I just crossed that one out. And actually 42, there should be, right? Yeah, 42. I just, right next to it, delete. The reason being, we have not covered this material yet. And this, as a review question, that wouldn't be fair. But I didn't redact it, so you can't see what it is. I just drew lines through it. So, I mean, if you really want to, you can go look up the information, acquire the skills, and answer the problem if you want. But it's not required on this exam because we have not covered that material yet. So we go down to 43. What does 43 have to say? 7.98 moles of sulfur trioxide contains how many oxygen atoms? Okay, we're given 7.98 moles of sulfur trioxide. Okay. How many oxygen atoms is that? First of all, we got to find out how many molecules it is. Then we can ratio the number of oxygens per mole of sulfur trioxide. So the conversion here would be, excuse me, actually there are two ways you can do this. You can say 7.98 moles equals of the molecule equals how many moles of oxygen. Okay, moles of sulfur trioxide. For every mole of sulfur trioxide, you have 3 moles of oxygen. Correct? Now that we've gotten rid of moles of sulfur trioxide, all we need is the molar mass of oxygen. I think that's a simpler way to do it. Yeah. How many oxygen atoms are there? Well, actually, that's as far as we need to go. I was reading something into that problem that doesn't exist. So how many oxygen atoms are there? Well, now we just need, for every mole of oxygen, we have 6.022 times 10 to the 23rd atoms. So 3 times this times, I've got your number. And I get 1.444166. 7 times 10 to the 25th. We do have to limit this one to 3. 1.44 times 10 to the 25th atoms. And there she blows. Okay, did I lose somebody? No, must have been something else. Some other program in the computer talking to us. 49. 4 molecules of chlorine weighs what? 4 molecules of chlorine. So what's a molecule of chlorine? That. Now, the giveaway is molecules. If it was just that, we would have said atoms. Chlorine is a diatomic, so it's going to be that. Okay. So we were nice enough to give you a hint. Molecules means more than one. So you just scratch your head and say, oh yeah, chlorine's a diatomic. So how much does it weigh? Right, we have 2 choices, grams or atomic mass units. All right, so we could calculate both ways. If we did 4 molecules, of this, right, and then did this one, then if we did this one in atomic mass units, we would say 1 molecule is how many atomic mass units? Chlorine, 35.45. 35.45 AMU. Remember, that value in there can mean 2 things. Actually, it's not 35.45, because that's just 1 atom. That's times 2. It's about 70, 70.5. So 4 times 70.5 is about 282 atomic mass units. Okay, so this one's the closest to that one. But if we do it in grams, no, right? Now think about it. How much does an atom weigh? Right? It's like extreme fractionals of a gram, right? So any of these that say grams, 142 or 284, it can't be. There's no atom that weighs that much. No molecule that weighs. This molecule won't weigh that much. Okay, so you can discount that method. Where you're headed for grams, no, can't be. So we have to use this method. So 35.45 times 2, and then times 4 is 284 atomic mass units. So there you go right there. So by process of elimination, we know that these are unreasonable. These 2 are unreasonable. So it's either this one, or that one. And actually, you don't need a calculator. Once you've eliminated these 2, you know that it can't be 18 atomic mass units because 1 atom weighs 35. Right? So that's impossible. So it's either this one or that. Well, if 1 atom weighs 35 and 2 atoms is about 70, but you need 4 of them, it can't be this one either. So process of elimination has to be C. All right. I have to scroll this one just a tad. Which represents the greatest mass? 53. All right. A is all the same. B is, they're 1 mole of each one. 1 mole of iron 1 mole of aluminum, 1 mole of rubidium, and 1 mole of titanium. Okay, since we've got the same number of moles of each element, what do we need to compare? No conversions required. All we need to do is look at the molar mass. Right? So 1 mole of iron weighs what? 5585, yeah. Okay. How about aluminum? 26.98. Rubidium? That's a
85.47.
uh-huh. And titanium, transition metal.
47.88.
Okay, so now all we have to do is do that. So rubidium is the heaviest atom. If there are equal numbers of them, it has to be the most mass. All righty, 53. How we doing on time? Okay, we're good. Let's see, I skip a few. All right, 61. A sample of metal weighing 2.59 grams. Okay, so our sample of metal weighs 2.59 grams. Combined with oxygen, the metal oxide weighs 3.01 grams. So the metal oxide, we don't know what the subscripts are here. Let's see, A, B. The metal oxide is 3.01 grams. The mass percent of oxygen in the compound is what? Okay. This should be fairly simple. Go back to your definition of mass percent. Percent by mass is equal to the mass of the element per mass of the compound. Okay. So what's the mass of the element? Well, we're looking for oxygen, right? If this is what the metal was before, and this is what the compound was after, how much does the oxygen weigh? It's this one minus that one. That's the mass of the oxygen. And this is the mass of the compound. Times 100. Okay? 3.01 and subtract 2.59. That's 0.42 divided by 3.01 times 100. So I get 13.95349%. They round it off to, well, that only gives us 2. So it's 14%. There it is right there. Actually, that's not right. It should be 14 only. Right? Because this subtraction only gave us 2 decimal places, 2 significant figures. So our answer can only be 14. So the test maker is wrong, technically speaking. All right, 62. What's the molar mass of nitroglycerin? C3H5, is it? NO3. Taken 3 times. molar mass. Okay, all we have to do is add up the molar masses of the individual elements. So 3 times 12.01, 5 times 1.01, 3 times nitrogen, 14.01, and 9 times oxygen. Let's see, did I do all those right? 3 of these, 5 of these, 3 of those, and 9 of those. Yep. So let's see. 36.03 is carbon. 5.05 is hydrogen. That one in my head. Okay, and 9 times 16. So I get 227.11. And there it is. Let's see. Would I need to round it off? No, because these are all exact numbers. So this is author's choice, rounding it off to 227. Okay, know what glycerin is? Have you ever used? I think sometimes they make it saddle soap. Glycerin. Glycerin is a carbon compound that's like this. Got the carbons hooked together. And then it normally has hydrogens here. 1, 2, 3, 4, 5. There's your 5 hydrogens. And then out here, it has, instead of glycerin, has hydroxyls out here, like that. But when you attach nitrogen to it, it goes oxygen, nitrogen. That. And then I think maybe like this. Okay, so that's nitroglycerin. It's very unstable. These bonds right in here are extremely unstable. So all you have to do is just kind of look at it cross-eyed and it'll explode. That's why Alfred Nobel was so keen to find a way to stabilize this stuff, because it had immense power, energy density, but it was very unstable. And in fact, his brother was killed in a manufacturing accident making this stuff. So eventually, he combined it with diatomaceous earth. They called it kieselguhr, and that stabilized it. As long as it's in that mix, absorbed by that stuff, you could smack it with a hammer and it won't go off. But if you ever find a box of dynamite, which is their trade name for it, a dynamite that it's old, and you open it up and you see these sticks of dynamite in there with liquid on the outside, this stuff coming out of it. Close the lid very carefully. Leave the building, lock it, and mark it for disposal by hazmat team, because that liquid in there will blow. And take the rest of it with it. All it needs is just get started. Just in case you ever stumble across this stuff. I think they still use it in the mines, dynamite. But they'll drill a hole and they'll put a stick of this stuff down the hole, and then they'll backfill it with ammonium nitrate. And that stuff with ammonium nitrate magnifies the force of the explosion by 10 times. I don't know what the exact number is, but it's massive. Okay, too much information? I just think it's fascinating. 63. All right. A certain compound has an empirical formula of NH2O. NH2O. That's empirical. Okay. Its molar mass is between 55 and 65. So the molar mass is less than 65 grams per mole, greater than 55. So somewhere in between. They want to know what is the molecular formula. So what we need is this multiplier, right? So we're going to need, definitely going to need the empirical mass. So nitrogen is 14.01, 2 hydrogens, and 1 oxygen. That's 3, 0, 8, 12, carry the 1. 3203 grams per mole of that formula. Our N value, our multiplier, can only be a whole number. So if it's 1, the value should be 32.03, right? Is that between 55 and 65? Nope. 2 times that is 64. There you go. Times 2. So this should be N2H4O2. Oops. I get that up there. B. B is our answer. So at first glance, you're thinking to yourself, well, it doesn't tell me exactly what the value is, so how am I going to answer the problem? So you have to say, well, you don't need to know. You know that the multiplier has to be a whole number. That's the key. 64. The molar mass of blood sugar, C6H12O6, C6H12O6. This is glucose, also known as blood sugar. That's the energy currency of the circulatory system. That's how cells of your the gut and the liver deliver energy to the rest of the body, predominantly. Also known as glucose and dextrose is what? Oh, okay. So we just need to calculate the molar mass of this thing. 6 times 12.01. Right? 12 times 1.01 and 6 times 16. Okay. And add those all together. Maybe I better skip the calculation and just go straight to the answer. 180.16 grams per mole. So it's not a light molecule. It's a pretty big molecule. In fact, it goes something like this. These are all carbons. There's a carbon up here. That group on it. And then it's let's see. OH, that's a carbon. Down, up, down. So there's glucose. It's a ring structure. Well, one form. Actually, that ring can open up. It opens up and closes at fantastic speeds. That's why glucose is a reducing sugar, because it can open up like that, and then the oxygen is free to interact with reagents, and that's how they. That's how your blood meter works. And the chemistry in the blood meter reacts with that reducing sugar, and it produces an electrical signal that's interpreted by the meter. Okay, let's see. 67. Percentage composition by mass of lead in, we want to know percent lead by mass. All right, what's this called? Well, if this is -1, that has to be +2. So this will be lead 2 fluoride, would be the proper name, the systematic name. But that doesn't answer the question. We've already got the formula. What we need is lead, which is what? Lead's right down here or something. 207.2. So it's 207.2 grams per mole. And then the total is 207.2 plus 2 times fluorine, which is 19 something, isn't it? Rounded off. It's a halogen. Far right.
18.8, so I guess it's 19.
19.00, yeah. Okay, times 100. And that should be 84.5%. That's why leaded glass crystal is so heavy. You've never noticed that. It sparkles too, because it's got all that metal in it. But leaded glass crystal is very heavy because that is a huge atom stuck in there. 7. All right. Let's see. Did I skip any? Nope. 75 has to scroll. Let's see. Yeah, we get 77 there too. 75. Calculate the number of moles of water molecules in 72 grams of water. 72. Oops, 72. And it's kind of redundant. Grams of water. So the number of moles of water. Grams per mole, right? So we know that water is this. We already calculated that once. So 18 into 72 is like 4. It's about 4. It's about 4 moles. Which one comes close to 4 moles? E does. Okay. So I didn't need my calculator for that. And 77. Determine the percentage composition by mass of oxygen in lithium sulfate. Lithium sulfate. Percent composition by mass of oxygen. So we need 4 oxygens in the numerator and the denominator. Plus, and we need sulfur, which is 32 something, 3206. 1 sulfur and 2 lithiums. 2 lithiums are pretty light atom. 6.94. That's why batteries now are predominantly made with lithium ion type, because you can concentrate more energy with a smaller atom. It's got the same charge as, say, sodium, potassium, rubidium, or let's see, what was commonly used before. Well, your typical dry cell has carbon in it, and it has manganese. It has some other metal, right? So it's really heavy for the amount of energy you get out of it. But if you go to lithium, you got a really small atom, so you can pack more energy into a smaller space. That's why lithium is in such demand. Anyway, do that calculation times 100. That should give us the composition of oxygen in that molecule. And it should come out to 58.21%. All right, let's see, 78 needs a scroll. A compound is analyzed and found to contain 12.1% carbon, 16.2% oxygen, 16.2%, and chlorine, 71.7%, 71.7%. And this is by mass. Calculate the empirical formula. Okay. We've done one like this before, it only had 2 elements in it. This one's got 3 elements. So this needs to be converted to grams. Grams. Right? Assume 100 grams, then this is the mass of each one. And then we can convert. Enter forward again. Take out the grams and leave us with moles. So for each mole, we have how many grams of carbon? Well, we have 1, 16 for oxygen, and oops, that's chlorine. 35, 45 for chlorine. Make that one memorized too. Okay, so this gives us the mole ratio of each one. It's going to be fractional though. Well, 12.1 here, 12.01 divided is 1.007. This one, you know what? We can shorten this one. That's about 1. This is about 1. This is about 2. So the ratio should be 1, 1, 2. Carbon, oxygen. There it is right there. Okay. Now, I could have gone through the trouble of calculating these and then ratioing them, but I noticed right away that these were so close that it's going to lead us to this ratio anyway. And that just saves you time, especially if you're in a hurry on a test. You can get to the answer really quick by estimation. Oh, 83, you have to scroll. All right, 83. You have 12.6 grams of an unknown substance. 12.6 grams of A and 35 grams of chlorine gas. 35 grams of chlorine gas, diatomic. Substance A contains 1.5 times as many molecules as chlorine gas. What is the identity of A? So when we say 1.5 times the molecules, so if we have A moles of this one, then it's actually equal to, excuse me, it's equal to 1.5 times the moles of chlorine gas. Okay. So the moles of this one, notice what they're asking us. An unknown substance has this mass, and all we need really is the number of moles. Because if we know the molar mass of a substance, we can usually identify what it is, as long as it's an element. Okay, so that's, well, okay, so we look at our choices. Our choices are compounds, and here's one molecule. Okay, so this could be a compound. How many moles is this? That's our first question. So how many moles of chlorine do we have? Grams per mole, 35, 45, 1. So we're going to have a little bit less than a mole of chlorine. Let's calculate exactly how much. .987. 0.987 moles. 0.987 moles. That times 1.5 is 1.481. That's moles of A. Moles of A. Okay. So what's the molar mass of A? It's grams per mole. So we divide this one, grams, divided by the number of moles, and we can get the molar mass. 12.6 divided into that, 8.51. 8.51 grams per mole. That's a pretty light. I did something wrong. What did I do wrong? 35 grams. That's right. But with 6 grams of this, 1.5 times as many molecules as the chlorine gas. So this is the moles. Yeah, that's right. 8.51 grams per mole. 1.5 times as many molecules. So we have 97 moles. 48 moles of this molecule. It's grams per mole. That's right. So it can't be oxygen because oxygen is 32. Uranium hexafluoride is out because uranium's, one atom of uranium is 238. Boron trifluoride, maybe, but 3 fluorines is 3 times 19. Carbon is 12, oxygen is 16. It can't be that one. Ammonia. That's the answer, ammonia. 14.01 plus 3.0. 3 is 407. 17.04. Something, I did something wrong. Let me see what it is. Oh, you see what I did? It has to be twice this. Okay. So 1.5 times 974 is actually half of this. 0.74 moles. 0.74 should be double this one. Should be 17.02. There you go. That's ammonia. That easy it is to make those mistakes. I use the molar mass of chlorine, but it's diatomic, so it has to be twice that. I'd like to say that it was a planned error, but no, I just goofed. All right, 83. '88 needs to scroll. Calculate percent composition by mass of magnesium in this compound. Okay. This is fairly straightforward. We've done one like it before. Magnesium arsenate. Right. Why do we write it that way? Because this is the 3- charge, and that's a 2+ charge. So we bring the 2 over here and the 3 over here. Okay, so what's the percentage by mass of magnesium? So 3 times Mg, 24.31. Three times that. And it has to be in the denominator too. So this is part of the total. And then 2 arsenics. Arsenic, I think arsenic is in the nitrogens. Yeah, 7492. And then 8 oxygens. 900. And that should be 20.8% magnesium. '97, chopped off bottom. There we go. None of these. Okay, whenever you see none of these, that means you have to do the calculation. Okay, convert 4.13 moles. 4.13 moles of PCl5. That's an equal sign. It's a very faint part of the equals. It's not a minus sign. PCl5 to molecules. Oh, it doesn't even matter because we're already in numbers. So the conversion factor is Avogadro's number. Okay. So what would be reasonable? Well, 4 times 6 is 24. So it's about 2.4 times 10 to the 24th. There we go. Right there. That's D. Let's see, going to be coming down to the wire here. 99. 5.392 grams of hydrogen gas. 392 grams of hydrogen gas. Contains what? We've got several choices. Atoms of hydrogen, molecules of hydrogen, atoms of hydrogen, atoms of oxygen. That's kind of dumb. I must have run out of choices. Put oxygen in here. Well, there's no oxygen to start with. right? We can't make something out of nothing. So we can throw E out. How about the others? Right? Are there any that really just are ludicrous? Are any atoms, hydrogen atoms doesn't weigh a gram. Right? 5 times 1 would be 5 grams of hydrogen. So we can throw A out also. That's just unreasonable. So our choices are actually B, C, or D. So we're going to have to go like this, grams per mole. And this is in terms of molecules. Molecules, hydrogen atoms. So once we find molecules, if our molecule answer doesn't match here, well, this one can't be it either. 5.349 moles can't be that. Or could it? 5.349 moles of hydrogen molecules? No, because the hydrogen molecule is 2 grams per mole. So this many moles of that would weigh twice that. Okay, so we're really looking at either B or D. Atoms or molecules. Right? So we got the same number. So how many molecules do we have? 2.02 grams per mole of the molecules. Right? So 2.02 into that is like 2.656. No, 646. Grams. Excuse me, moles. That's moles of hydrogen molecules. Right. So convert that to molecules. 6.022 times 10 to the 23rd would be about, let's see, 3 and 15, about 15 times 10 to the 23rd, or 1.5 times 10 to the 24th molecules. 1.5. I did something wrong. 1 second. Let me just do the calculation. 5.392, 2.02 grams per mole of hydrogen gas is 2.67 moles of the gas. And then molecules of the gas would be 6.022. Avogadro's number. Yeah, okay, I did it wrong. 1.607 times 10 to the 24th molecules. Okay, so it can't be hydrogen molecules. For each molecule of H2, we have how many H's? 2. Oops. Backwards. Numerator, denominator. 2 to 1. So 2 times that would be 3.22 times 10 to the 24th hydrogen atoms. That's how we get the right answer. Did I confuse anybody? Okay. $100. Consider equal mole samples of dinitrogen monoxide, laughing gas, aluminum nitrate, let's see, potassium cyanide. Rank these from least to greatest number of nitrogen atoms in each sample. Okay, equal mole samples. So let's just say we have a mole of each, right? 1 mole of each one. Right? So which one has the least to the greatest? Nitrogen. We got 1 nitrogen here. We got 2 there. And we got 3 here. Okay, that was pretty simple. Calcium cyanide, laughing gas, and aluminum nitrate. Okay. Temptation is to make it more complicated than it is. The key is that same number of moles of each compound. So now all we have to do is just figure how many nitrogens in each molecule. So you got to be able to write the molecules. We've got to write the formulas. That's the key to this one. 101. Calculate the mass. 101. 3.53 times 10 to the 26th atoms of silver. Right? We can't go from atoms to mass. We have to go from atoms to moles. Right? Then we can go from moles to mass. We just need the mass of silver. Mass of silver, 107.87. Grams per mole. So 3.53 to the 26th power, 6.022, third power, and then 107.87 times. 6.32 times 10 to the 4th. Okay, here we are. There it is right there. What if it had put the answer in kilograms? What would it be? Grams to kilograms. Right? 10 to the 3rd grams, 1 kilogram, 1,000 grams per kilogram. Right? Then this one, that one would have been 1, it would have been 63.2 kilograms. Those are the type of sneaky things that test makers do. All righty. 106. Down to the wire. The mass in grams of 3.52 moles of nitrogen gas is what mass? Mass in grams of that many moles. Okay. So we need moles here, grams here, and 1 atom is 1 mole of nitrogen is 14.01. So both of them together would be 28.02 grams. So 3.5 times 28 would be, let's see. 4, and then half that. 98, about 98. There it is right there. Okay. I'm rushing to complete it before 11 o'clock. 110. What I was supposed to be in. Am I? Yeah, Just got those last two. There you go. 110. Oops. Getting faint. Wrong color. $110. Calculate the molecular formula of compound with an empirical formula. There. There we go. CH2O is the empirical formula.
CH2O means
And we need our multiplier. Molar mass of 180 grams.
180 grams per mole is the molecular.
Molar mass.
Now we need the empirical mass to get our ratio.
So let's see,
Carbon is 12.01 and then 2.02 for hydrogen and 16.
right, so we got what, 2030.03. Right?
0.06, 7, 8, 9, 10 carried 1, 3. Okay, so we divide by 30. So that should be about 6. So C6H12O6,
Probably glucose.
here it is.
Okay. And go over this one. 13. $60.2 milliliter sample of mercury.
60.2 milliliters of mercury
Has a density of 13.6 grams per milliliter. How many atoms of mercury? So we got the volume, but we need the mass. So how do we get the mass out of this?
We need to get rid of milliliters and leave us with grams.
Well, there it is, 13.6 grams per milliliter. So 60.2 and 13.6 is
818.72. 8. Try that again. Grams. Okay.
now we can find out how many atoms.
Grams. First, we need moles. And then we need to convert moles to atoms.
So what's the molar mass of mercury? Let's see.
$200.59.
Okay, so the rest is number crunching. 200.59 and 6.022. So I get 2.46 10 to the 24th.
Atoms.
Let's see. There it is right there. All right, I think that's it. Nope, one more. Vinegar. Now, technically, this is wrong. Vinegar is a mixture of acetic acid and water, 5% acidity. But the molecule we're talking about here is acetic acid. And the acetic acid is carbon, hydrogen, oxygen in these ratios.
40.1% carbon, 6.70% hydrogen, and the rest of it is oxygen. Okay, so how much oxygen? 40.1 and 6.7, correct? Yeah. Let's subtract that from 100. 53.2. There we go.
40.01, I don't know if that'll matter.
Oh, 0.01, yes.
It could matter. Let's try that again.
40.01 and 6.7 is what we know. Subtract that from 100. 53.29
Or 53.3. Let's make it 29. There we go.
Now, if the molar mass of vinegar is 60, what's the molecular formula? Okay, I'm already past time.
We would just say this is grams, right? 100 gram sample. Then we would convert that to moles so we can get the molar ratio of the atoms in the molecule. Oxygen 16.
Then we would ratio those, and I might as well do it. 40.01, 12.01 is 3.33 moles of carbon, and then 6.7, 1.01 into that is 6.63, and then 53.29 divided by 16 is 3.33. So we can eyeball this one. The ratio here is 1 to 2 to 1. So carbon, hydrogen, oxygen. And we need the multiplier. So what's the molar mass of CH2O? 12.01 for carbon. 2 hydrogens is 2.02, and 1 oxygen is 16. 30.03. This is 30.03 grams per mole. And the molar mass is 60. So 60 divided by 30 is approximately 2. So it's C2H4O2 is the molecular formula for acetic acid, essentially. Now, usually, since this is an acid, we usually write it this way. There's the one hydrogen that dissociates in aqueous solution. And then here's the rest of it, C2H3O2. Because these hydrogens don't dissociate. And this, if you look it up in your polyatomic ion, this is acetate. And that makes 8 becomes ic. That's why it's acetic acid in solution. Okay, I think that's it. Yeah, that's all I have marked anyway. Any questions? We've already lost one. Must have had to go. Well, if there are no questions, then we'll see you on Tuesday.